So this is now our lecture on Wiedemann-Franz law, which is an empirical law relating the thermal conductivities and the electrical conductivities of metals together in a given temperature. So we will have just one slide of a lecture slide. So I think this lecture will be actually like bearably long. And why we are covering this Wiedemann-Franz law here is that essentially we can also derive this, or at least we can understand the results that we have based on the just derived Trude-Sommerfeld model. So essentially the free electron model that we have been covering here at this point in our chapter. And this free electron model can be used to explain and understand the Wiedemann-Franz law that we will be outlining to you soon. And that's essentially the Wiedemann-Franz law is an empirical law, and it's quite old one. So it was found already during the 19th century by G.H. Wiedemann and Robert Franz. And essentially, this is based on measurements on experimental data. So they did not come up with this law by making derivation, making up initial calculations or pen and paper, like a theory derivation, but rather they discovered that metals seem to be complying this law. So hence it's an empirical law. And they found essentially that for all metals, this proportionality applies, so that we have the kappa, which is our thermal conductivity of our piece of solid, and then we have sigma, which is our electrical conductivity. So this ratio between kappa and sigma, the thermal and electrical conductivities, equals to a constant known as the Lorentz number L times the temperature of our piece of a metal. And this was discovered by the two gentlemen outlined, so Wiedemann and Franz. And there, the nice thing of this is that it does, like, first of all, of course, like it explains that in a piece of a metal, the electrical conductivity and thermal conductivity, they are being highly affected by the fact that there are free electrons, so that there are conduction electrons that can transport both of these quantities. So both thermal radiation inside the object from a point A to point B, plus also the electrical current can be transported by similarly the conduction electrons. And here the Lorentz law is of a form that we have pi squared divided by 3 times the Boltzmann constant kBt squared divided by the elementary charge E squared. And L comes from the fact that the temperature dependence of this Wiedemann-Franz law was discovered by Lorentz. And that's the name why we have this Lorentz number named after Lorentz. So this is all that we have regarding the Wiedemann-Franz law. It's an empirical law. And the nice thing is that it really relates the thermal conductivities with the electrical conductivities. And essentially, for example, tells to us that if we have a metal and a given temperature, and we would know the electrical conductivity, we could estimate what is its thermal conductivity. And also it, for example, would say that if we have a good electrical conductor as a piece of a metal, for example, copper is pretty good electrical conductor, we know right away that also copper should be pretty good thermal conductor as well. So these are the kind of insights that we can derive and come about with when we remember the Wiedemann-Franz law. So that's why it's a nice piece of equation to remember. It's not that complicated, so we all can remember that. And its meaning and its potential usefulness in terms of estimating the properties of metals. So this is what I want to say. I think this is my record, less than 5 minutes long lecture. So I'm pretty happy of myself. And please continue with me for the follow-up lecture that won't be, unfortunately, 5 minutes long. So I thank you your time and patience. Thanks and bye-bye.